Okay, in this exercise we are looking at a Bayesian analysis of cloud kitchen sales using R. So this is from an actuarial exam paper from May 2023 from the Indian actuarial exams. The exercise introduces actuarial students to Bayesian statistical models using R. The task involves analysing sales data from a cloud kitchen where total monthly sales are assumed to follow a normal distribution with an unknown mean and variance. Students will compute the moment generating function for the prior distribution, derive the posterior distribution of the mean sales, and visualize both prior and posterior distributions using the code provided. So there's some code given in the exam paper and you just have to work from that to generate a plot. Okay. So the total monthly sales on a particular cloud kitchen follow a normal distribution with an unknown mean theta and a variance 20 squared. Sales x1, x2, etc., are observed over n months. Prior believes that theta follows normal distribution with mean 60 and variance 5 squared. And sales for the last 5 months are extracted for analysis, and then the total sales for the last 5 months were 340. Okay. So what we're going to do here is start off with the moment generating function. So let m of theta t denote the moment generating function of theta. So state and compute the first derivative of theta of m theta evaluated at t equals 0, and the second derivative of the moment generation function m of theta evaluated at time 0. A little bit tricky, but essentially this is the expected value of x and the expected value of x squared. So we're going to denote them m1t0 and m1t0 for the first one, which is the expected value, and m2t0, which is the expected value of x squared. Okay, so we'll set it up like that. So just as I sort of said, the m1x0 is the expected value of x, and m2x0 is the expected value of x squared. The variance is the difference of the expected value of x squared minus the expected value of x to be squared. So equivalently, we can generate m2x0 equals the variance plus the expected value of x squared. So the prior mean and the prior standard deviation is 60 and 5, which is given in the question. So m1x0 is the prior mean, and m2x0 is the prior standard deviation squared plus the prior mean squared. Okay, so that's just sort of using a setup for the random variables, as you probably would have learned them, and also moment generating functions. So we're piecing a couple of things together there regarding random variables. Okay, so let's just evaluate it there. m1x0 is 60 and m2x0 is 3,625. So essentially just a theory question, just sort of see, do you spot the relevance of a couple of things? Okay. So, exercise B, state the posterior distribution of theta and compute parameters of the distribution using the sales from the last 5 months. After 50 months, the analysis is performed using 50 months of sales data. Total sales in the last 50 months were 3,400. Compute the parameters of the posterior distribution of theta using 50 months of data. Remark. So what are we doing here essentially? This is an application of Bayesian inference to update the probability distribution for the mean sales of the cloud kitchen based on new data. Okay, this exercise demonstrates how to combine the prior distribution representing initial beliefs with the likelihood function based on observed data to form the posterior distribution. Okay, so theta follows n with a mean of prior mean and a variance of prior variance. Okay, so it's a random variable that follows a normal distribution with theta and equals the mean and the variance. Okay, so the posterior mean of theta follows a normal distribution with the following parameters. Now this is where we get into a lot of Bayesian statistics theory. So there's two sort of very cumbersome formulas here. So the posterior mean and the posterior variance. Okay, so the posterior mean is n times the sample mean divided by the variance plus the prior mean divided by the prior variance divided by n divided by the variance plus 1 over the prior variance. Bit long-winded, but actually it just sort of, we have all the building blocks already, so just how to piece them together. So it's a fairly long and complicated little formula that we're going to build, but it actually is built up, constructed of very straightforward components. The post-variance is something similar there. N divided by the variance plus 1 over the prior variance, and get the invert that essentially. Okay. So for the last 5 months, N is 5 and the sample mean is 350 divided by 5, which is to say that is the monthly mean, okay, for 5 months. And the standard deviation is 20. So the posterior mean is just using that formula there, post underscore mean, and it is just using all those building blocks and piecing it together, plus the information that we have found previously, the prior mean and the prior standard deviation. Let's just go back there a second to see where we got those. There we go, those ones there again. And build up the expression for the posterior mean and the posterior variance using those expressions, those terms. So we end up with a posterior mean of 61.9, a posterior variance of 19.04, and the square root of that posterior variance, which is to say the posterior standard deviation, is 4.364. Okay. So what we're going to do now for 50 months as well, we're just going to swap out the sample means and the sample sizes. So sample 1 underscore mean becomes 3000, it becomes sample 2 mean essentially in the formula. That is 3400 divided by 50, and the sample size there is now N2, which is 50. So essentially we're going to set up post 2 underscore mean, which is actually just using the same formula as previously, just with slightly different terms. And also the posterior variance, post 2 underscore var, which is again the same expression as previously, just with updated terms or amended terms. Okay, so the posterior 2 mean is 66.06, the posterior 2 variance is 6.06, and the standard deviation of posterior 2 variance, which is the standard deviation, that is 2.46. Okay. So on to the next question. We are given some code to help plot the prior distribution of theta. Use the code below to plot the prior distribution of theta. So we're given x coordinates, which we will build our plot from, 60, which is the prior mean, plus a sequence from -3 to 3 by 0.2. So that's a sequence from -3 to +3 in jumps and steps of 0.2 times 5. Now, the relevance of that 5 is that it is the prior variance, okay? Or the prior standard deviation, I should say. So, y is evaluated as d norm of x, so the density function, the likelihood of each of those values of x, when the mean is 60 and the standard deviation is 5, okay? And plot x and y with y limits from 0 to 0.02. Okay. The question goes on to asks us to add a line to overlay the posterior distribution of theta after 5 months, and then add another line to overlay the posterior distribution of theta after 50 months, and then comment on the plot. Okay. So let's just look at what we were told to start off with. So this is the code that we're given, and remember that 60 is the prior mean and 5 is the standard deviation, is the prior standard deviation. Okay, and we're going to plot it there. I just additionally put in plot character equals 18 and color equals red, just to make it a little bit easier to follow. So we're going to do the first exercise now, which is to overlay a line that corresponds to the posterior distribution of theta. So we have px1, which is the posterior mean, plus the sequence from -3 to 3 in increments of 0.2 times the square root of the posterior variance. That's the analogy, that's the equivalent of times 5 in the previous example. Okay, so yeah, that's just actually the x coordinates to help us map out the plot, and then we're going to create the y coordinates from that. So d norm of px1 with a mean of the posterior mean and the standard deviation, which is the square root of the posterior variance. And here we're going to add it in with lines px1 and py1 and color it in green. Okay, so this is our plot overlaid on the prior distribution. Green doesn't come out well, but it's better than I still like to have it color coded. Hopefully you can pick that up there. You can tell the distinction between the prior distribution and the posterior distribution. Okay, so what we're going to do now is overlay another line to overlay the add another line to overlay the posterior distribution of theta after 50 months. So this is posterior mean 2, okay, and posterior variance 2. So we're going to take the same approach again, create px2 and py2. That is the coordinates of the x-axis and the coordinates of the y points, the height of the curve, the likelihood of the curve at each of the x coordinates using d norm. So d norm px2, and the mean is posterior mean 2, or post2 underscore mean, and standard deviation equals square root of post2 variance. This time we're going to color it in blue. Okay, so lines px2, py2, color equals blue. And there we have it there. It sort of peaks around the 65 to 70 mark. It's probably closer to 66 actually. Okay, and it's much higher. It has more altitude and much narrower. Okay, so that's grand. Comments. First scenario, the sample size equals 5. The posterior distribution with sample size equals 5, which is the 5 prior months, is closer to the prior distribution. There is a slight shift of the mean towards the sample mean and a similar dispersion. Okay, so yeah, it's close enough. Now there's a bit of a shift between the red dots and the green line, but you know, nothing major. Well, a little bit, but noticeable, but nothing major. When the sample size increases, the posterior distribution moves towards the sample mean and variance dispersion. More weight is given to the sample when the sample size is big. Additionally, the variance is reduced from a larger sample size. Okay, so that's the sort of remark on the peakedness and the narrowness of the blue curve. Basically, more, how should I put it, more data involved there. Okay, so that's it. We'll leave it there.